All right. Let's begin with a word of prayer. Dear Father, we thank you for today. Again, Lord, I thank you for these students. Pray with us today. Help us to prepare for the test Thursday. And I just pray that you help us to use this time, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So, do you guys have any questions? Oh, today's a test, right? That's right. I should have committed to that joke more at the beginning. It would have been more believable. Yes?
On the practice test, there was a section finding the definite integral. Will we need to know that for the test?
No, we haven't covered definite integral yet this semester. So if there's let me get right to that. At the was it the example? I think I posted a video. If you've looked at the YouTube channel, the last thing I posted, I think I have something circled. I made an arithmetic mistake in the last problem we worked, so beware of that as you're looking at your notes from last time. The thing I did at the very end, it basically it was a factoring mistake. Like I factored out a half, but then instead of factoring, I multiplied or vice versa or something like that. So there's an arithmetic mistake towards the very end of the last example we did. All right. I assume you're talking about test 3 from last year? And its solutions here. Let's see here. These all look fair, except, question 8. We haven't gotten to that yet. Yeah, question 8 is not on this test. That'll be on the final, but not this test. So, yeah.
The final is everything.
Yeah. Final's cumulative. It'll include this question 8, among other things.
The only thing that we have to learn is question 8, like that stuff.
Well, I don't know. That depends on who you are.
So we're going to go over more.
I mean, what do you have to learn? I mean, I can't answer that. I don't know. I know for myself, I have many things to learn, but yeah, I know what you mean. I would just be a jerk. Let's see here. The course planner's not there. A reasonable question. I will give you a somewhat reasonable answer in as much as I'm capable of today. In a minute. Excuse my voice. I'm still getting better, even though it doesn't sound like it. I am actually feeling better, believe it or not. Ugh. All right, so was Thanksgiving yet? Oh, why can't you see it? Same old reason. VGA. Come on. So we are approaching test 3 on Thursday, right? Like it says, up through 6.2, which is use substitution, right? Then after this test, we'll probably cover 6.3, 6.4, 6.5, 6.6, 7.1, and these sections here. I mean, parts of those sections. We'll see what we actually do there. So this would be the material that's on the final, but hasn't been tested on test 3. So like basically the end of chapter 6, a token section in chapter 7, and then those first 3 sections in chapter 8. You'll don't be scared of this. This is actually really, really easy material. It's not bad. So, and it actually helps us review the first part of the course again, believe it or not. But yeah, the final's comprehensive. It'll be a little bit of everything. So anyway, enough about that. Let me put back the was it quiz? Oh man, what I got too many things open. I don't know what I'm doing. We don't need advanced calculus. We don't need complex. We don't need. You certainly don't want to see that. You don't want to see that. We got plan. Go away. All right. Here we go. So again, this was the problem they were just asking me about was problem 8 on test 3 is on integrals that have, you see these numbers? This would be like the area from 5 to 6 between y equals 2x minus 9 to the fourth in the x-axis. I talked about that a little bit, but we haven't covered these kinds of problems yet, so that's not on the test 3. Problem 8 you can skip for now. Okay, now that we got that settled, is there anything earlier on the test you guys like to talk about, or just other generally? Homework 13, 5 and 6. All right. Oh, let me be lazy here. It's gotten more difficult for me to do things, you see. I did something to my computer, as you might be able to tell. See what happens if you try to shove a folder between your screen and the keyboard? And like, this folder won't go in my bag. And then all of a sudden, I open it, I'm like, I do have a new computer, I just need to start using it. I can still type, it's just kind of painful. Let's see here. 13, number 5, and 6, right? Come on. It's thinking. It's thinking. Here's number 5, although I think you probably can't see it worth anything. Make it bigger. Big enough? All right, so I guess your question is how to work this out, or we have the integral of the square root of x plus 1 over x, put some big parentheses, minus, what is that? I can't, 4e to the x, okay. Okay, so first of all, we can break it up into 3 integrals, right? This is the integral of x to the 1/2 dx plus the integral of dx over x, if you like, minus 4 times the integral of e to the x dx, right? Using properties of the integral, indefinite integral in this case. Indefinite just means no, they're not numbers here and here, and you know, like that problem 8 we were looking at. And it also means it's a notation for a whole class of antiderivatives. But anyway, basically just remember to add a constant at the end. Otherwise, I'll take off a point, whatever. Add 1. We get x to the 3/2 over 3/2 plus the natural log of the absolute value of x minus 4 times e to the x. Now, how do I know that? These are the basic antiderivatives we're supposed to know. Like, so integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus a constant, right? The integral, on the other hand, of, and this is for n not equal to minus 1, right? The n equals to 1 case is this, right? Which we could rewrite as this. And it turns out that that's if I want something I can differentiate to get back to 1 over x, the natural log of the absolute value of x will do it. And so these are basic formulas we must know. All right, the integral of e to the x dx is e to the x plus a constant, because if I differentiate e to the x, I get back e to the x. And what's the other? Is there anything else we know? Is there some other function we know how to integrate? Not really. Not that I can remember anyway. I'd like to say sine and cosine, but we talked about that. I'm not allowed. So barring u substitution, that's it, right? So this is 2/3 x to the 3/2 plus the natural log, the absolute value of x, minus 4e to the x plus a constant. There you go, that's the answer. Which, I'll see. Oh man, we're back to that stupid. Hey, didn't I talk about this the other day and we had. That's weird. No, it is the case. I mean, we don't disagree. It's really a question of notation. This is, in fact, an identity. So it's not a different answer, right? But, yeah. I think absolute value bars are better. So. But like I told you guys, that's not something I really wanted to test on this test. It matters for the definite integrals. I'll show you guys why next Tuesday, most likely. Okay? Number 6, find f by solving the initial value problem. All right, so we have f prime of x is given, and f prime of x is what is it? 6x squared minus 6x. And what else do we know about this mystery function? We know that f of 3 is 33. All right? The question then is to find f, basically. Now, they said, solve the initial value problem. That's just a different way of saying the same thing. So I know the derivative of a function. I know one of its values. It turns out that that's enough information to reconstruct the function. So if the function's derivative is 6x squared minus 6x, what does f of x have to be? Here's a way to think about it operationally. F of x should be the integral of f prime of x dx, okay? That's not quite true because, I mean, it's true provided we choose the right constant in the indefinite integration, all right? But I'm just going to write that in here for you guys because it's a useful way to think of it, all right? So basically integrate whatever the derivative is that you're given. So we know how to do that, right? That's a straightforward calculation. I integrate 6x squared minus 6x dx. What is that? 6 times the integral of x squared dx minus 6 times the integral of x dx. What's the integral of x squared dx? It's x cubed over 3, right? What's the integral of x dx? We add 1 plus 1 is 2, x squared over 2, right? I hope you guys are following me here. Where did those come from? I just used the power rule for an antiderivative, for an indefinite integral right here with n equals to 2 and then n equals to 3. Well, n equals to 3 is, yeah, n equals 2, n equals 1 rather. N equals 1 gives me x squared over 2. N equals to 2 gives me 2 plus 1 over 2 plus 1, x cubed over 3. Are we, let me stop talking. Do you agree, disagree? You guys with me? Okay. And then we can clean this up a little bit, right? This is what? This is 2x cubed minus 3x squared plus a constant. Now, how do I figure out what that constant is? F of 3 is 33, right? So it means that constant doesn't have the freedom to be whatever it wants to be. It is forced to be a particular value by this piece of data right here. Now, 2 times 3 to the third power minus 3 times 3 squared has to be equal to 30, plus a constant has to be equal to 33. But what is this? 54 minus 27 plus c. So c is equal to 33 minus 27, it looks like, which is what? That's 6. So therefore, f of x is equal to 2x cubed minus 3x squared plus 6. Two x cubed minus 3x squared plus 6. Okay, good. Whew. That's good. I mean, I was worried. Now, suppose you don't trust me. Suppose I'm in some sort of insidious cabal with the designers of WebAssign to teach you a wrong answer. I mean, you could just check it, right? Plug in 3. Does it give back you 33? What happens if you plug in 3 to my boxed answer here? Plug in 3. I get 2 times 3 cubed minus 3 times 3 squared. I get 54 minus 27 plus 6, which again is 33. Also, if I differentiate my answer, what do I get? 6x squared minus 6x plus 0, which gives me back that f prime, like we started with. So, to summarize, to solve an initial value problem, integrate the derivative you're given, right? Then apply the initial condition, whatever it is, and that will allow you to choose the value for the constant that gives you the answer. It's this two-step process, these problems. Does that make sense? I know we haven't spent a lot of class time on these yet, but so I appreciate that question. Do you want me to work another one? Oh, 7? Is the 7 another initial value problem? Yeah, we can work that out. Sweetly. Find f of x. Excuse me. Unpleasant. Let's see here. Oh, why am I using this thing? Ugh. Oh man, you guys should see the Calc 3 test I'm giving later today. Oh, it's a good test. I'm happy about this test. It's good. I got it out of my system for them, so your test will be easier, right? F prime of x is equal to 2e to the x minus 4x I don't know, it's kind of debatable, right? A lot of you guys want to be doctors, so if you do calculus wrong, maybe you kill somebody, right? If they do calculus wrong, maybe a bridge falls down. I mean, which is worse? I don't know. I guess you're probably not going to directly use calculus, though, right?
The bridge is worse, more people will die.
The bridge will kill more people. I should be meaner to the bridge builders. Yeah. Okay. I'll accept it. I'll accept it. Let's see here. F of 0 is equal to 8. It's really not a fair characterization of my Calculus 3 class. There's not many civil engineers in there, I don't think. If any. Do we have civil engineering? I don't know. I don't remember. Okay, so step 1, integrate. So this is the integral of... Okay, so I'll break it into pieces. This is 2 integral of e to the x dx minus 4 times the integral of x dx, right? So I have 2 times e to the x minus 4 times x squared over 2. How do I know that? Again, I'm going back to these things we must know. N equals to 1 gives me x to the 1 plus 1, which is 2 over 2. X squared over 2 is the integral of x. So there you go. This is our template, which we can fit a whole multitude of initial conditions to, right? Like this answer, so far, actually allows me to put any initial condition I like. That's why we add the constant, basically to allow for different possible initial conditions. Now, I have f of 0 as 8, though, right? But what else is it equal to? It's also equal to the formula evaluated at 0, which is 2 times e to the 0 minus 2 times 0 squared plus c. What is e to the 0? It's 1. And that's, so I get 8 is equal to 2 plus c. So c is equal to 8 minus 2, which is equal to 6. Oh man, c is 6 again. What the heck? Therefore, f of x is equal to that. I mean, it's very boring. What's going on here? C is not always 6. This is just coincidence. I'm sorry, I don't mean to. Yeah. Should we scroll down and see if I'm right? Yep. Next? Yep.
Mark 12, number 30.
Un momento. Let's see here. By the way, don't ever send me messages through WebAssign. If you have a message for me, you should send me an email. I never check WebAssign messages. I already have 3 emails. I don't need another one to check, you know? So, it's like, just send me an email. All right, yeah, sorry, I got distracted. No. Yeah, preview frame. Which one was it we were asking? Ah, yes. E to the 1 over 3x, how do we differentiate that? I suppose the short answer is carefully. The longer answer is by the chain rule. So if you don't see how to do a derivative, right, if you're not sure about something, the way I approach it is like this. Okay, so d dx of, let's list a couple chain rules while we're at it. What's the derivative of u to the n with respect to x? It's n u to the n minus 1 du dx, right? That's the pattern. If I was to differentiate with respect to x the natural log of u, how's that work? Well, that turns out to be du dx divided by u. That's the chain rule for that one, right? The chain rule for the exponential function is just e to the u times du dx. So these are some things that you want to have internalized and know. Uh-oh. Let's see here. So we're trying to differentiate e to the 1 over 3x, right? So the pattern here is that that's e to the 1 over 3x times the derivative with respect to x of 1 over 3x. Right? In other words, u is 1 over 3x in this case, right? Are you okay? Yeah. See, I can never get context because I know the minute I do, like this eraser dust, it would get into the context. I think that would be bad. I feel like that would be hurtful. I do need glasses, so let's see here. This is what? So I've got 1/3 minus 1 over x squared.
How are you getting the negative 1 over x?
Okay, so if we differentiate with respect to x, 1 over x, this is the derivative with respect to x of x to the minus 1, which is minus 1 times x to the minus 1 minus 1.
Oh, okay. So you don't do just a normal chain rule where it's e minus like the derivative of.
Oh, I suppose you could. You like.
But that's what I was doing, and I wasn't getting.
Well, if we do that,
But
it should be the derivative with respect to x of 1 times x minus 1 times the derivative with respect to x of x, all divided by x quantity squared.
but
Oh, I just wanted to work on I just factored the 3 out. You may put the 3 back in? I could do that. So this, of course, is 0. And this is 3, so I get minus 3 over 9 x squared, which is minus 1 over 3x squared.
Okay, I see what it is.
But yes, of course, we don't need to. I mean, that's fine. I have no objections to using the quotient rule there. It's just I'm trying to tell you it's not necessary because it can really just look at it as an n equals minus 1 differentiation, right? It's just power rule with n equals to minus 1. But it's good to be able to see things multiple ways, because that means if you forget one, you've always got the other to fall back on, which is, I think, one of the wonderful things about math, right? If you really understand differentiation, you can do a problem about 3 or 4 different ways sometimes, right? If you're in a history class and they ask you when did the Battle of Hastings happen, if you don't happen to know, it's too bad for you. I mean, you can't derive that, right? I mean, I guess if you knew the order of things, maybe you could. If it was multiple choice, I don't know. There's still study strategies, but you won't be surprised when I tell you math is better. Okay. I'm meaning to get a bumper sticker for my car. Math, only subject that counts. Yeah, that's not mine. It's pretty much the only funny bumper sticker I could find online. I spent some hours looking. Yeah. What's that? It's the same one, number 5?
No, number 5, like, homework 12.
Oh, this is homework 12. This one?
Yeah.
Sure. Oh, yeah, that's right. This is on the test, too. Man, I almost forgot. We did do that, didn't we? What is on this test? I mean, math. How much we can be sure of? Yeah, optimization. The basic algebra of logarithms could be on there too. I might ask you a question that's just about properties of exponentials and properties of logs. Maybe the graph of the exponential, the graph of the logarithm. Those are fair test questions. You need to know your basic exponentials and logs. I mean, we spent about 20 minutes of class on that, but it's there. Anyway, this one here is an example of an absolute extrema problem. These kinds of problems are there's a few steps, right? Number 1, we find all of the critical numbers in the interval of consideration, right? Number 2, you evaluate the function at the critical numbers and also at the endpoints. And number 3, you pick a winner and a loser. That's pretty much it. So let's see here. So let's find the critical numbers. H of x is, what is it? e to the x squared minus 1, right? All right, so are there any critical numbers? Well, look for dh dx is what? 2x e to the x squared minus 1. So by the way, sometimes I find it more convenient if I'm differentiating e to the u, I will sometimes write the differentiation rule like this. Du dx times e to the u. Sometimes it's more convenient to look at it with the factor on the left rather than the right. I mean, I don't know. I wrote it on the other side over there, but multiplication commutes, so you could do it either way. Now, if this is equal to 0, that's the condition we need for a critical number, right? Place where they have a horizontal tangent. There's no places where the derivative doesn't exist here because this function is differentiable everywhere, so we don't have to worry about places where the derivative doesn't exist. That's not an issue. In fact, that's almost never an issue for your problems. How can we get that 0? How about the exponential? Can it be 0? That's why I said I want you to know the graph of the exponential. The graph of the exponential looks like this. It's positive. E to the u is greater than 0. Think about u equals to x squared minus 1. Doesn't matter what x squared minus 1 is, that doesn't change the fact that when you plug it into the exponential, its output is positive. So the only way that can be 0 is what? If x is 0, right? So 0 is the only critical number. All right. So that's step 1, is I found all my critical numbers. Step 2, evaluate f of x at endpoints and the critical values. I probably gave you a different, I'll make up a new numbering every time I talk about this. This numbering is not like written in stone or anything. It's just, you know, let's see here. So f of 0, f of minus 1, f of 1. Those are the contestants in the absolute extrema game here. One of these will be the winner. It's kind of like, let's see here. So f of 0 is what? Which function do I plug into? The derivative or the function? I plug back into the function, right? That's what we're talking about in terms of being the largest or smallest. So f e to the 0 squared minus 1 is e to the minus 1. All right, f of minus 1 is what? It's e to the 0, which is equal to 1. And f of 1 is also e to the 0, which is also 1. Now, e to the minus 1 is also 1 over e, which is approximately 1 over 2.71. Da-da-da. So what's the minimum? What's the maximum? Yeah, these are the max, right? And this right here is the min. So we attain the maximum at the endpoints, and the minimum value is reached at 0. Well, plus or minus 1. I guess they kind of give away the structure of the answer right here, didn't they? That's kind of a nice hint. Funny. Any questions about this kind of problem? Do you understand what you have to do? You have to find the critical numbers. And then check the value of the function at the critical numbers, check the value of the function at the endpoints. And then there's this wonderful theorem of analysis which says that the minimum and maximum of a continuous function will be attained. It will be reached at one of the points that you looked at right there. There's no danger. These problems always have an answer. There's always the biggest one and the smallest one. Other questions? Oh, we worked this problem before. It's where we learned that if we drink, we should drive right away. Remember this problem? Too bad we couldn't have done that on the CFA day. Oh well. No, I probably shouldn't do that. You guys already discouraged me from my interpretation, so it's good. You guys are more level-headed. You're probably not Trump supporters. Probably not. What? No? You guys like Trump? I don't know. Just checking. Go ahead. Yes. Homework 8 from number 13. Soitin. Oh, I'm sorry. I said something. Homework 8, number 13 is what I did. Yeah, that sounds like something I might have said. All right. Homework 13, number 8 would be much more interesting. All right, let's see here. There. Man, I love integration. It's so much fun. Physics. Now you guys are making me work. All right, fine. You guys and your love of real world problems. So annoying. So this is really just another another initial value problem. So what's the relation between velocity and position? How are they related? Yeah, exactly. So say if you use the velocity, let's suppose s is the position, right? Just to give letters. Then what's the calculus that relates these two symbols? It's that ds dt, right, is equal to v. So in other words, to get v, I can say that's the integral of ds dt. Again, with the understanding that in order to pick a specific velocity function, I need an initial position to fix the constant, which is going to come from this indefinite integral. All right, so this one, I'm given that the velocity at time t is 7 times the square root of t. I'm fixing the bogus notation that they're using in the WebAssign problem. I don't know what this f of t is. Nonsense. It's v. It's the velocity. So v of t is 7 times the square root of t from 0 to 30. What else do we know? Ah, there we go. What's that?
So you know that there's going to be an x with every number. Since s of 0 equals 0, then there's going to be like 2x plus 2x squared plus 2x. There's going to be
Not yet. I'm trying to figure it out. Me not understanding it doesn't mean that what you said doesn't make sense by any means. I mean, it could just be me.
No, what I'm saying is there's not going to be a constant.
Oh, right. Absolutely. Yes. This will fix the constant value. I totally agree with that. So the solution, so v is equal to the integral for us of 7 square root of t dt. And so what's that? That's 7 times the integral t to the 1/2 dt, right? What's the integral of t to the 1/2? Oh, you guys are way ahead. So you're doing 2/3 t to the 3/2, yeah. Plus a constant. So in other words, v of t is, its generic template is 14/3 t to the 3/2 plus a constant. Now this allows for all different sorts of initial conditions, right? But we know something else. We know that, oh, you were confused with good reason. I'm sorry about that. I mean, I made this mistake on purpose to see if you're paying attention. So this is S. Come on, right? There's I mean, you can look at this in terms of U substitution, right? So like, if v is equal to ds dt, right? Check this out. Here's another way of thinking about it. That tells me that ds is equal to v dt, right? So the integral of ds is equal to the integral of v dt. The integral of ds is just s, so s is equal to the integral of v dt. As a way of thinking about what we're doing in terms of U substitution kind of logic. Anyway, my silly comments aside, this is s of t. S is a function of t. All right. Now, I don't know. All right, so s of 0 is what? 14/3 0 to the 3. What's 0 to the 3 halves power? 0, very good. So this is just c again. So c apparently is equal to 0. Woo. So s as a function of time is just 14/3 t to the 3 halves. And there you have it. That's the position as a function of time. Yeah. Oh. Huh. Let's see, do we have some graphing questions in the homework? Surely we must have. Yeah. Which homeworks are on this test, by the way? Let's see here. Did we already cover homework 9 on test 2? Yeah, so homework 10 was the, let's see, let's look at 10 for a second.
No, I mean, are you going to ask us questions with graphs with the actual model going on?
Possibly, yeah. But here's a graphing question. I mean, like, this is a really nice kind of question. This is a total gift if I give you a question like this. Like, here's a graph. Find the coordinates of the absolute minimum or absolute maximum if they exist. I mean, I'm almost kind of embarrassed to ask this question. I think this is insulting. I think this is maybe too insulting to put on the test. You should be offended if I put this on the test, really. Right? You'll get over it. Yeah, it's what I figured. You guys. This one's a little bit more respectable. There is no absolute maximum. There is no absolute minimum here because it asymptotically goes like there is no end, right? So in terms of the whole function, it goes. You pick a value negative as you like. If you get close enough to the asymptote, it's there, right? It's unbounded below. And likewise here, the maximum that you like to say, the maximum value is 1, right? But the value 1 is never attained by this graph. So the maximum doesn't exist either. So this is a graph that has neither an absolute maximum nor an absolute minimum. And yet, it does have a critical point, looks like right here. Yeah, but that's actually a saddle, as it happens. It's not it's a saddle point. It's not a maximum or a minimum. Anyway, that's not even part of the question. I'm just talking. Don't forget this problem, right? Remember how we set that up? That kind of problem? Yeah, I think we want to maximize the area for a given length of fence, right? So the setup for this problem, it depends on the nature, right, of the word problem itself. But for this one, the length of fence, the fence length is what? It is, I've got 1, 2, 3x lengths, right? 3x plus y, exactly that. And then usually you're given some particular length of fence, whatever it is. You guys, I mean, it depends on the nature. I forget what the problem says here. I mean, what's the length I'm given? Oh, I'm given 2,820 yards.
Can those cows swim?
See, yeah, like, but what's the? Yeah, that. See, my problem was much cleaner. I mean, we had lava, we had children. It was. Or I'm sorry, students. I was bounding students by a lava river. Yeah, this graphic lacks a certain imagination.
Narrow, though.
It is a really sad river. Maybe there's like very very. It's full of piranhas, and they're leaping piranhas. They'll just, you know, eat the meat right off the cows if they like walk over it or something. I don't know. But this, and then of course the area is what? Well, this case is not x times. Oh, yeah, you're right. It's x times y. It depends on the setup, right? And then of course you can either use x or y as a variable. Basically, if I solve this for y, it gives me y is equal to 2,820 minus 3x. Then you take that, you plug it over in here, and then you have a is equal to x times 2,820 minus 3x. Then what do? You solve dA dx equals to 0, which gives you, this is what? So that gives you 2,820 minus 6x, so x is equal to 2,820 divided by 6. That's your one critical value. That should give you the dimensions, which maximize the area. To actually find the dimensions, I have to take that number and plug it back into the y formula, right? And then I have x and y, the dimensions that are needed. But in real-world problems, be aware, sometimes you have to think about endpoints for real-world problems, right? If you're working with a population, populations can't be negative. Maybe you're working a problem about maximizing something, and it involves temperature in a room, and you're given that the temperature in the room is between 60 degrees and 80 degrees. So maybe like 60 degrees and 80 degrees are the endpoints for your problem, just like the absolute extrema problem. Maybe you have to plug in 60 and 80 and then find any critical numbers that are between critical temperatures, in that case, between 60 and 80 for whatever you're maximizing, deliciousness of a cup of coffee or something. I don't know if we could find some sort of mathematical measure of such. But so just to give you a quick review of the graphing, I want you to know I'm just talking about the basic graphs of, can I erase? Everybody got what they need to from this already? Okay. So, what does exponential graph look like? It looks like this, right? What's the natural log look like? It's a reflection of this across what? The line y equals x, right? So basically, if I have a point on the exponential graph that's, say, a comma b, there's a corresponding point, b comma a, on the natural log graph. So that geometrically corresponds to a reflection over the line y equals x. So for example, this point here is 0, 1, right? What's that get reflected to? 1, 0, right? Yeah. So these are things we should know. And so there's y equals ln of x, right? And there's a lot to see in this graph, right? Like you can appreciate d dx is equal to e to the x. What does that say? The slope of the exponential function is equal to its value at every point. As the exponential gets larger and larger and larger, the slope of tangent lines to the exponential graph gets more and more and more and more extreme, right? And likewise, as you go to minus infinity, the slope of the exponential function kind of goes to what? It goes to a horizontal line, right? So the slope of the tangents to exponentials are 0 as you go to minus infinity. You can also see that. You can appreciate the interplay between the graph and the calculus. Likewise for the log. How does log work? d dx of the log is what? 1 over x, right? And you can see all that. If you look at the slope, what does the slope of the tangent line look like for the natural log? First of all, it's always positive, right? Natural log is always increasing. It's always got a positive slope. But if you look at these little and think about tangent lines, right? What happens? As you go further and further out, what happens to the log's tangent line? It gets more and more and more shallow, right? So the slope of the tangent line goes to 0 as x goes to infinity for the log. You can see that, right? On the other hand, it becomes a vertical line as you approach the x equals to 0, right? I'm just saying you can appreciate these things, how they're put together, right? You don't just have to memorize a graph of an exponential or log anymore. There you have other things about calculus, that can weave these ideas together for you.
Would you give us a point on a graph, say e to the x and then x is for the corresponding one for ln of x, and just have it split?
That might happen. Yeah, like if I tell you that, for example, 1e is on the exponential, what's the corresponding point on the log? Right? And what does that mean? The natural log of e is 1, right? Of course, you also need to know these guys, right? Right? And, always popular. Or but for the second equation to make sense, that stuff has to be positive. We haven't talked about it much today yet, but what was the other thing that happened? Right, didn't we do... Oh yeah, U substitution. I was thinking about implicit differentiation, but we already did that, didn't we? Oh, I guess the difference was we have not yet done explicit... We might do implicit differentiation, but what's the new wrinkle? We can revisit that topic, but what's the difference? Now I could ask you something like e to the xy is equal to y, find dy dx, right? That's now a problem that I can ask you. Yeah. How would you do that? Differentiate, right? Both sides with respect to x. Here I have e to the xy times the derivative with respect to x of the inside function. So what I have is I have y times e to the xy plus x e to the xy dy dx is equal to dy dx. So then what do we do? We isolate the dy dx's, right? Nothing really new there. It's the same thing we did before. It's just now we have the derivative of the exponential function to add fun to the problem. Or we could differentiate natural log as well, right? Logarithmic differentiation, that's definitely something we haven't tested yet, which will be tested, right? What does it mean, logarithmic differentiation? If I say use logarithmic differentiation to calculate blah, 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 what does that mean you have to do? You take whatever you're given, take the natural log of it, right? You differentiate that, and then you solve for dy dx. We did a bunch of these. I was going to remind you, kind of getting back to Megan's question about like how will you test about natural log or exponential. Here's one way I might do it. You know, sometimes rather than just saying collapse the log, I'll just say, okay, here's an expression. You can reduce it to natural log of x to the a, y to the b, z to the c. Find ABC for me. And that makes the grading much easier for me because I can just go and look and go, aha, a equals 1. Or if you have a not equal to 1, then I know you did it wrong. And I don't have to worry about, oh, did you interpret it differently than I might have meant to be? I mean, I just take all the interpretation out of it. What does it mean, collapse, expand, whatever? No, this is what it is, so you can try to match, and when you match, then you got it. So, excuse me. Is there any U substitution in this test? Maybe not. Oh, here's an example. Part D is an example of logarithmic differentiation. Now, I didn't say do logarithmic differentiation, right? But actually, to calculate the derivative of this, I kind of like this problem because it allows me to test logarithmic differentiation without being a jerk about it. Like, I'm sometimes not happy about the question where I say, uses logarithmic differentiation to calculate such and such, and then the student just does ordinary differentiation. And then I'm like, oh man, now I gotta take off points, and I feel like a jerk when I do that. This, on the other hand, I feel like a nice guy because the only way you can do this is to do logarithmic differentiation, right? So I don't have to be a jerk about you following directions or not following directions. There's only one way to do it. So you take the log, use properties of log, pull out the x, then differentiate. Solve for dy dx. I don't know if there's U substitution on this test. Oh, there it is. I'm an idiot. Yeah, apparently there is. Well, wasn't I a nice guy? I even told you guys to do U substitution last year. I see I'm getting too nice. I should just be like, integrate. Haha. No, that's no fun? Well, I mean, there's really kind of only two cases in here. It's either one of these basic things like we did today, or it's a U substitution. That's kind of all we got.
But the length of the test, is that how long it's going to be?
Approximately, yeah, something like this. How many questions? Enough. And I don't know, I haven't written it yet, but I'll figure something out. Anyway, I'll let you guys go. If you have any questions, I'll stick around here for a couple